Good morning, and welcome to this fourth edition of the Great Designs in Steel technical webinars. My name is Brian Esterberg, and I'm the Senior Automotive Market Strategist at the American Iron and Steel Institute. Before we start today's presentation, I just want to be sure to remind you to mark your calendars and register for Great Designs in Steel 2025. It'll take place May 21st in Novi, Michigan, and registration is now open at greatdesignsinsteel.com. Today, it's my pleasure to welcome our guest speakers, Tom Wormald, Principal Projects Manager, Steel Solutions, and Parth Patel, Project Manager, Press-Hardened Steel at ArcelorMittal Global Research and Development. Today's presentation is Press-Hardened Steel and Automotive Applications. Your microphones have been muted for today's presentation. I'll ask that you please use the Q&A feature in Zoom to submit questions throughout. We'll not be using the chat or raised hand feature today. Again, please use the Q&A feature and submit questions throughout the presentation. My colleague, Hesham Ezzat, our Senior Technical Advisor, will join Tom and Parth after the presentation to address your questions. A recording of this presentation will also be made available. It's now my pleasure to welcome my friend and colleague, Tom Wormald.
Welcome, everyone. Happy to be joining everyone this morning. Today's presentation will touch on many topics related to press-hardened steel, also referred to as PHS. The intent of this presentation was to address many frequently asked questions about the grades and the hot stamping process, but also feel free to contact myself or Parth with any inquiries you might have after the conclusion of today's session. We'll touch on topics such as simulation, part design guidelines, welding, and corrosion. We'll finish with a brief overview of some of the newer technologies related to hot forming of steel. I'll be starting off the presentation, then handing it over to Parth Patel for the second half of the talk. So I'd like to start with an introduction to ArcelorMittal's press-hardened steel grades and a few words on the nomenclature used, specifically for those who might be a little less familiar with these products. Usabor and Ductibor are the trademark names for coated press-hardened steel produced by ArcelorMittal worldwide. The values following the name refer to the target tensile strengths for each of the grades after the forming and quenching process, ranging from 450 to 2000 MPa. Usabor and Ductibor vary in the type of applications where they're commonly used. Higher strength Usabor for anti-intrusion applications to minimize deformation, and Ductibor to retain ductility for energy absorption applications. Typical fracture strains are also shown on the slide, quite high for the Ductibor family, where higher deformations are expected, and more modest for the higher strength Usabor. These values are developed from lab testing and verified at the part level to ensure accuracy in real-world scenarios. So I'll now provide some details of the hot stamping process that is applied to parts manufactured from the PHS family of steels. The direct press hardening process involves heating the blank up to 930 degrees Celsius and performing the forming and quenching process virtually simultaneously in a water-cooled die. Recommended parameters vary by PHS grade. The guidelines shown on this slide apply to our Usabor 1500 product. Enabling the phase changes and making sure they're complete throughout the process is an important part of establishing the hot stamping parameters. Two ways of viewing the process are shown on the slide. On the left, this is from a kind of a part progression standpoint, and on the right, more of a metallurgical view. The indirect process, which we'll not be addressing in detail today, is not as common, but is still used by some customers, and involves separating the forming and heat quenching steps of the process. In that approach, the part is formed cold, and the heating and quenching are performed afterwards. As mentioned, the hot stamping process is largely driven by the desire to ensure complete transformation of the microstructure of the steel. A window of time and temperature is established to ensure complete austenitic microstructure is reached in the heating furnace. Transfer time is minimized between the oven and the press, an automated system that occurs in a matter of seconds. A critical component to achieving consistent end properties is controlling the cooling and quench rate in the die, and that's guided by the CCT diagram you see on the right. A rapid cooling rate is required to ensure complete transformation to high-strength martensite by the end of the forming process. The thickness of the blank also affects hot stamping, as a thicker blank logically will retain heat and influence many of the factors we just discussed. There are many advantages to utilizing hot stamping technology in automotive applications, both in performance and manufacturing. Key is the ability to stamp very high-strength steel components with complex shapes not possible otherwise. Said another way, there's no longer a need to sacrifice part strength for challenging part geometry. Dimensional accuracy, particularly for the strength of the parts, is achieved as springback is all but eliminated. Press force is lowered in the direct hot stamping process as the actual forming action occurs in the heated, lower strength blank. The hot stamping process is well suited to the use of laser welded blanks, providing an opportunity to mix PHS grades and thicknesses to optimize and tune performance as needed in a particular area of the vehicle architecture. And finally, sandblasting of scale developed in the hot forming process is completely avoided through the aluminum silicon coating applied to ArcelorMittal's usable and ductile steel products. So we'll go through a brief review of applications for press-hardened steel, and I'll highlight a few of those applications that are most commonly considered in vehicle design. So combining press-hardened steel grades as laser welded blanks provides flexibility for the vehicle designers to tune that performance and achieve significant mass savings. Usable and ductile steel grades can be combined to provide both energy absorption and anti-intrusion performance, specifically where they're needed. Through ArcelorMittal's multi-part integration, or MPI solutions, components are combined into a single hot stamping to significantly decrease part count, as well as reducing the quantity of spot welds required for vehicle assembly. MPI applications can be applied in areas throughout the vehicle architecture, including the dash panel, rear H-frame that includes the rear rails, and the classic door ring applications already in production for more than a decade. On this slide, in lighter and darker orange are shown some of the common applications for press-hardened steel grades in an automotive architecture. Very high-strength usable at 1500 and 2000 MPa is often considered for the protective safety cage around the passengers, regardless of the class of vehicle being developed. Ductibor with higher ductility after stamping is normally applied in areas where they could benefit from controlled displacement and crush, such as the leading portions of the front or rear rails or the lower portion of the B-pillar to achieve a desired bending behavior inside impact. Those two applications, front rails and B-pillars, are also perfect examples of where laser welded blanks are applied for part consolidation and efficient load transfer. The higher strength of the press-hardened steel grades achieves mass reduction not only through thickness reduction, but also through the elimination of reinforcements. That mass reduction can often meet or exceed 20% compared to baseline designs. Shown here are a few applications of the usable product, both at the 1500 and 2000 MPa level, along with some typical thicknesses. More and more applications are opening up to the possibilities and benefits that can be achieved through the application of grades from the PHS family of products. Accurate predictive simulation of PHS steel products is obviously a key supporting technology for the use of the various usable and ductile products. The simulation of PHS in stamping and performance is somewhat specialized, reflecting some of the unique attributes of the products in the hot forming process. ArcelorMittal works closely with the leading software companies to support hot stamping simulation and continuously improve the accuracy of the predictions. For manufacturing, specialized material cards have been developed for each PHS grade that are both temperature and strain rate dependent. Many common process parameters need to be adjusted for hot forming process, including the friction between the blank and tooling. More advanced material cards have been developed to support detailed representation of the phase and phase transformations that occur during the process. For performance characterization of the grades after the hot stamping process, we include strain rate effects, failure modeling, and even a small Bakart effect observed with the material. Perhaps unexpectedly, the representation of PHS grades in a vehicle assembly can actually be viewed as less complicated than cold stamp steels, as the influence of work hardening are avoided. Only thicknesses need to be mapped to key final parts where that level of accuracy is needed. Experimental formula curves have been developed at representative temperatures for the hot stamping process. Unlike cold stamping, a widely accepted formula doesn't exist for estimating the FLC, such as the Keeler equation, so the appropriate formula curves are a necessary component of the material card itself for simulation. With an increase in thickness and temperature, there is an improvement in the forming limit curve. It's largely up to the user to choose the preferred temperature for evaluation of the results, and that's commonly between 600 and 800 degrees Celsius. In developing the experimental FLCs, it's been found that both user bore grades, the 1500 and the 2000 MPa, show actually quite similar forming limits during stamping. Friction values. Friction values to be used in simulation of the hot stamping process are an area of development and research. Friction values are certainly much higher than the 0.1 to 0.15 values that we're used to for cold stamping. For hot stamping, accepted values tend to range between 0.35 and 0.5. Preferences certainly exist by user. They're established through their own experience in correlation to stamping results, usually involving blank movement and thinning. ArcelorMittal has tended to find increased accuracy with somewhat lower friction values within that range, but it's especially challenging to identify a single value for friction with all the variables that exist in the hot stamping process. An accurate representation of the overall hot stamping process is also required for simulation. A prescribed temperature is often the starting point, namely the exit temperature from the furnace, 930 degrees Celsius in this example. Transport time can be 5 to 10 seconds, depending on the method used for transporting the blank. Efficient manipulation of the blank and press movement is key for ensuring an adequate temperature is maintained for the actual start of the forming and quenching process. Designing parts for the hot stamping process does require adhering to some design rules that I'll briefly review before handing things over to Parth. When designing parts for the hot stamping process, it's important to understand some of the unique considerations required. Direct hot stamping certainly allows complex shapes to be formed that would not be possible with cold form steels at strengths near those of the finished PHS part. As mentioned, optimum performance is achieved when high temperatures can be maintained for the blank at the beginning of the forming. One important guideline is the fact that the forming is required to occur in a single punch stroke. Particularly for user-board products, the quenched material is high-strength martensite, and therefore further forming operations should not be considered. Thinning values, whether measured or predicted through the simulation, are a strong guide for developing successful stampings. In addition to the FLD, a maximum thinning guideline of 20% is often applied to ensure successful stampings and avoid issues in performance. Controlling wrinkling in the hot forming process is one of the key challenges. As blank holder force control and draw beads are avoided, wrinkling is controlled with die geometry, and therefore strong communication between the part designer and manufacturing is strongly recommended. Die spotting is particularly important to ensure effective quenching of the entire part and avoid soft zones. Tool temperature is also a key variable that can often vary between approximately 80 and 150 degrees Celsius, depending on several factors, including the flow of the water into the dies. Many design guidelines for PHS parts emanate from the need to have good tool to blank contact and quenching. A minimum 3-degree draft angle is recommended, with steep walls making quenching less efficient due to the reduction in contact pressure. Large radii are recommended, the standard recommendation being to keep a minimum of 5 millimeter radius. And as subsequent flanging operations are not possible for the high-strength PHS grades such as Usibor, those same flange features can often be designed right into the draw geometry themselves. One of the potential drawbacks of using two smaller radii in the hot stamping operation is illustrated here. It's possible for the coating to actually penetrate the relatively soft steel substrate at these high temperatures, creating indentations as shown in this picture. This phenomenon is avoided by following the recommended guidelines we just spoke about for minimum radii. So in these pictures, you see how the coating has actually penetrated into the steel substrate, creating this sawtooth pattern that you see in all the pictures labeled from 3.5 to 4.5 millimeter radius. At 5 millimeter and greater, that sawtooth pattern has been completely avoided, sort of backing up that 5 millimeter rule of thumb as being very important for part design. Blank holders that are commonly used to control material flow in cold stamping are likely to cause issues in hot stamping by promoting early quenching on the binder surface. A gap is usually utilized instead to allow the flow of material into the die. Now the gap value is commonly 0.2 to 0.5 of the blank thickness and can be adjusted as needed. Using gap control can make stampings more prone to wrinkling, but there are certainly geometry adjustments that can be made, including changes to the radii and wall angle. For some selected part geometries, crash forming with no blank holder whatsoever is even used in the hot stamping process. So at that point, I'd like to hand over the presentation to Parth to discuss some other aspects of press-hardened steels and the hot forming process.
Thank you, Tom. Appreciate. So today I'll be discussing some of the key issues in the PHS or key applications, especially in the welding terms or corrosion, those kind of issues. So basically, again, I'm not going to address every topics in the welding. Basically, I'm going to discuss just some of the myth that we have. I'm no welding expert, but I'll try to cover as much as I can. So again, we have UC-bore and ducti-bore. That's a direct hot stamping process we use, as Tom explained earlier. Both are aluminum silicon coated, and they are available in AS 150 and AS 80 coating weights. Again, the coating transformations are very similar for UC-bore and ducti-bore. There's a myth in the industry that the product is different, the carbon percentage is different for UC-bore 1500 or 2000 or ducti-bore. The transformation would be different, but actually that's not the fact. The fact is aluminum transformation will be very similar. Sure, the microstructure is going to be slightly different. It's for ducti-bore, sorry, UC-bore, it's going to be fully martensitic, but for ducti-bore 1000, it's also fully martensitic structure. What happen is when we supply a raw material to the hot stamper, they received in a LUC coating, and when they start heating in the oven, transformation occur. When it's fully alloyed, it looks like similar to this in the picture. Let me just point out. So this is what it looks like, and you will have ideal interdiffusion layer and a fully alloyed coating. And this is what in the welding guy or assembly, that's what you're gonna deal with it. And that's the key. So that's why we are saying weldability is influenced by coating and ultimately influenced by the hot stamping condition. So we have to keep in mind that hot stamping conditions really matters for the welding. So again, another myth is, like I said earlier, people think that coating is different, so it's gonna have a different welding parameters. But like I said earlier, your UC-bore and ducti-bore has a very similar coating. So if you look at this chart, in this chart, what we are trying to show is your electrical contact resistance for aluminum silicon and GI coating. It's much more than GI coating. It's almost 25 to 30 times more than GI coatings. So it has a good electrical contact resistance, and that's why it will generate more heat. While if you look at the bulk resistivity, which is for the base metal, usable 1500 and 2000, it's a very similar. It's not that much difference. So the key message here is your coating really matters. So your hot stamping process really matters, and that's what one of the message I would like to say, that for PHS, if there is any welding issues or something, you may want to look at how your coating looks like, how your ideal looks like, and that's kind of more important. But the key message for our material, for usable 1500 2000, it's very similar, despite having a different carbon percentage. But again, there are many parameters that you have to take care for the welding, not just resistivity. Moving on to weld growth. So if you have a similar resistivity for coating, right? So your parameters should be very similar. So if you're doing a homogeneous welding for usable 1500 to usable 1500 or usable 2000 to usable 2000, your welding parameters should be very similar to each other according to the weld diameter you want to get it. So like I said, your coating really matters. So if your coatings transformation is very similar for each material, then you will have very similar process parameters. And like I said, there's a myth in the industry that 1500 and 2000 going to be very different. But if you're doing homogeneous, it's very similar. If you're doing heterogeneous, could be different cases because you're adding a new surfaces now, so different coatings, right? So that's gonna matter. Another things I just want to quickly touch upon is PHS grades the weld strength. Obviously TSS at tensile shear stress, because this is all fully martensitic. Ductile 1000, 1500 and 2000 is fully martensitic. We haven't seen any effect of the carbon, but for cross tensile test, it has an effect of the carbon. As carbon percentage increase, Ductile 1000 has around 0.1, this has a 0.22, usable 2000 has around 0.34 typical value. And as carbon percentage is increasing, your cross tensile test is decreasing. Now, it has correlation with your toughness of the weld, which I'll be discussing in the next slide. So again, just quickly touch upon hardness, because there is most of our martensitic product, which is Ductile 1000, usable 1500 or usable 2000, it's all fully martensitic product. Only difference is a different carbon percentage. So the phenomena of the hardness is very similar. You will have a drop in hardness in a soft zone area. Obviously softening is occurring because the heated areas are below AC1 temperature in this zone. But there is a myth. So again, weld hardness depends on a carbon percentage. As you increase your carbon, you're going to have high hardness. But there is a myth that cross tensile test or shear tensile test fail in a haze area or soft zone area. It doesn't actually do that. Actually, it fails in the nugget area, as you can see in the picture, where the hardness is really high. Why it's happening? Obviously, you have a fresh martensite in the nugget zone area, and this fresh martensite actually was a low toughness. So when you have a low toughness, failure usually occur in the nuggets, right? And this is for cross tensile test and shear tensile test cases. So that's the logic behind this one. So again, in industry, there's a lot of myth that is gonna fail in haze area, but in reality, it will failure occur in the nugget area. Quickly jumping on a corrosion issue, obviously a lot of newcomers or a lot of new OEMs or somebody who's new to hot stamping, they always wonder that why do we use LUC coating? Why not we can do the hot stamping without LUC coating? So obviously, to avoid a scale, if you're using uncoated steel, you will have a lot of scales during the heating process, and that will create a problem. So you want to avoid those scale issues. You want to avoid decarburation issues. If you heat them at high temperature, you're going to lose the carbon from the surface, and that will make this decarburation issues. Another issue is obviously corrosion issues, health and environmental issue, because if you're using uncoated steel, you will have to use a shot blasting. It will create a lot of health and environmental issues. The other thing is, if you're using shot blasting, it might have a geometrical distortion in the part, and that might create another issues. And that's why we need this aluminum silicone, coating for the hot stamping, so it can avoid the scale issues, decarb issues, any other shot blasting issues, right? So why LUC? So LUC is one of the, how do I say, it's the best performing for perforated corrosion. If you see, so again, this is a test which is VDA 233-102. It is a scratch test. Basically, you put a scratch in the steel and in the coating, and you measure the depth of the corrosion after 12 weeks. There's a spec says 6 weeks, but we have done some of the harsh environment. It's a cyclic corrosion test, and you have a multiple acids and stuff and all, and then when you measure the depth, actually for UZ board, it's actually less than the zinc coated steel. So perforated corrosion wise, it is acting better than the zinc coated. Of course, it's better than uncoated material, but it's much more better than zinc coated as well. So there is perception that GI is better than LUC. Actually, for perforated corrosion, it's much better than GI coating. If you paint the samples, again, this was an unpainted sample as stamped. You stamp it and you just do the test. But if you actually do the testing on a painted samples, your depth of the pitting corrosion is less than 50 micron, which is much less compared to other products in the market. So yeah, the message here, again, the myth is like LUC is not better than GA. That's a myth. It's perforated corrosion is much better than GA coated. Yes, for a cosmetic corrosion, it's different issues, but for perforated corrosion, this is one of the best in the class in the market today. Quickly jumping on environmental and cycle issues. Again, I think it's already very well known that PHA is going to reduce the part weight because it's a high strength. So you don't need to wait. Let's say if I'm comparing with the DP600, I'm saving a lot of weight here, almost 26% weight. But what does it mean if I reduce the weight? How it's going to save the CO2, right? So this is a good article from APNT, and what they have shown here, I'm not going to go in really details. Just quickly, to discuss that. Steel actually produce much more CO2 compared to the hot stamping process itself. So here you can see in the graph, for 1 ton, I think it's 12 kg CO2s, and for same thing for B pillar, if you want to process B pillar in the press hardening oven, it's only 0.65. So you see the huge difference between steel making process and hot stamping process. So if you're using, let's say, DP600 or some other cold stamp, you're gonna have to use more weight because material utilization rate is low. You're gonna have to use higher mass. So if you use higher mass, you're gonna produce more CO2 because you're producing more steel, right? And that's why you need PHS. So you can reduce the weight, you can reduce the CO2 amount as well. Just quickly discuss our XCAR product. We're offering this XCAR product. It's a recycle and renewably produced product. Basically, this product, again, right now we're comparing with a multi-piece. So if you produce separate pieces, join them together, and if you compare with MPI, Tom just discussed about MPI products in previous slides. MPI is nothing but we are combining multiple parts together and we are integrating them together. It will help to reduce the weight as well as it helps to reduce the CO2. So compared to our MPI, it's minus 14%. But if you use XCAR product, it reduced to minus 31%. So it's too much, it's a really high ratio when you reduce CO2 percentage. We have right now usable 1500 available for XCarb, which is almost 20% of our MPI products. It is available in North America as well as in Europe. Quickly jumping on new materials. So right now, obviously, industry is going through a lot of challenges like reducing cost, carbon footprint. You need to integrate more parts. A lot of other challenges coming in, but every challenges has opportunities, and that's what we're bringing in the market right now with the new products, new solutions. But same thing with MPIs, there is also some challenges like heating challenges, transfer challenges, quenching challenges. Heating challenges, if you have uneven thicknesses, and which I'll be discussing in thermo boost part, how it can help you. So those challenges, considering those challenges, what we want to do is we have introduced this product Ductile 1000. It's in the market for a long time, but again, just to rephrase, this is best in crash ductility. It is 1000 MPa product. It's a high strength material. We have done, there's a lot of papers been published by Waterloo and other entities that when you compare crash ductility with DP600 or other material, it's really equivalent or one of the best in the class at this strength. So, and the other one is it has no problem with the spot weld issues because it's a low carbon product. we don't see much issues with the spot weld either. So it's one of the best PHS product for the spot weld. There is no delayed fracture with the mechanical trimming. So there are people who's using mechanical trimming after hot stamping. So that's something is possible. And obviously, it's an energy absorbs part. Ductibor, as Tom mentioned earlier, Ductibor is more for ductile, and this has a local bendability in the product. So it's more suitable for the frontal member area. As you can see in this Xiaomi SUV7 example, Ductibor 1000 is used in the frontal crash, and that can replace materials like aluminum, which is much more costly, and that can really help increase the safety of the car. And it can be also used for B pillars or cross members or rear rails, those kind of applications. It's available in most of the region. It's industrial in North America, Europe, China, and it saves 20% compared to DP600. Usable 2000. So that's another product that we have in the market, and it is again it's one of the highest strength steel in the market today, available for automotive steel, and it's ultra fine grain metallurgy. It has maximum local ductility in crash, and it resistant to hydrogen embrittlement. Again, if you look at this chart in the picture one, after quenching, obviously in hot stamping, you heat the oven in the oven, and then you take it 900 degrees Celsius. You're going to have some absorption of hydrogen at the hot stamper. Typically in industry, it's 0.2, 0.3 ppm diffusible hydrogen. In UCBO 2000, we have seen, at least from last 2 years, 3 years, the experiments we did with hot stampers. We work with a lot of hot stampers, and we haven't seen, I think, more than 0.25, if I'm not wrong. Again, we always recommend to control the dew point, but our message here is, if you bend the material in 4-point bending test at 1200 MPa strength, and even if you have 0.5 or 0.55 ppm hydrogen concentrated diffusible hydrogen in your material, you still are good. You're above the limit, because in assembly stresses, it's less than 1200 MPa. But there is a perception, or there's a myth in the industry that UCBO 2000, since it has a high strength, it's going to have a hydrogen embrittlement issues. Actually, it's less susceptible to hydrogen. So it's a very myth. People just assume that there is a problem with the material, but there is no issues with the hydrogen embrittlement. Again, this is targeted for anti-intrusion parts like A pillars. Especially you wanna see this case where this car Zeekr got into accident with a big trailer, and you can see the A pillars stay intact, but the trailer got bent. This is UCBO 2000 for you, and there are many other applications for sure. Door beams, roof rails, and other stuff, right? Again, this is going to save almost 10% compared to UCBOR 1500. It has a higher strength compared to UCBOR 1500. It's available in almost all the region right now, and it's ready to approve by many OEMs. Quickly jumping on thermo boost, as I discussing in my earlier slides about challenges with MPIs and other. Obviously, you have a different gauges with MPI, right? But the problem for hot stamper, the challenge for hot stamper is how do I heat them uniformly, right? If I have a patch here, how do I heat them uniformly? If I have 1 mil material and 1.8 mil material, how do I make sure 1 mil doesn't increase my interdiffusion layer, and 1.8 mil also heated uniformly? So we have this proprietary paint formulation that apply on the line after LUC coating is done on the line, and it's basically degradable paint, and it reduces the heating time. Obviously, the paint's going to absorb more heat, and it's going to heat faster. And that will increase the window. Once you have reduce the heating time, it will increase your processing window. It will also reduce your hydrogen intake, because it spends less time in the oven, right? And since it's degradable, like I said, once you heat them in the hot stamping oven, it will all the black paint will evaporate. You won't have any black paint. You will have the same part, exactly the same part as in your UCBOR process, current UCBOR process. So it will have equivalent welding behavior, corrosion resistance, and adhesive bonding performance. So the material will remain same, but it gives a lot of benefits. So somebody who has challenge with dooring, double doorings, or multi-gauge thicknesses or patch, this is the product that we have in the market. And obviously there is going to be more products coming into market. And with that, this is the last slide, I think. If you have any question.
Thank you, Parth. Thank you, Tom. This was really very informative. I would like to remind the participants to kindly submit your questions through the Q&A application at the bottom of the screen. Okay, so let's go to the Q&A. We have a question regarding the thickness. So to Tom and Parth, what is the highest thickness possible for PHS?
I can take that.
Sure.
So yeah, we have again multiple thicknesses available across the region, depending on the region, what region you are in right now, right? And depending on a grades for PHS, let's say for UC Board 1500, we have also in North America different gauges available from 1 to 2.3. In other region, we have different, depending on a grade. If you're looking for UC Board 2000, we have 1 to 2 mil available right now. Ductile board, we have different gauge, but yeah, it's depending on your grades, depending on your region as well.
Yeah, and I'd add, I think we'd strongly recommend you contact ArcelorMittal if you're at the extreme lower or extreme higher end of the range that Parth just mentioned. For a lot of reasons, availability is obviously something that you'd want to confirm. Making sure that we're talking about the Usabor product, the coated PHS. Different PHS, like an uncoated PHS, does have a different thickness availability. And finally, for any steel grade, there's always a width to thickness capability that you want to be aware of. And that goes for whether it's PHS or cold roll steel. So that's something you could certainly discuss with your local ArcelorMittal representative, or send Parth or I a note.
Great, thanks. You just answered the question that I was going to ask, Tom, relative to coil width, because as you and Parth had indicated, with this MPI approach, and with all the efforts to try to integrate a lot of parts, the question is, how wide can you get a coil to be able to address some of your needs? So as Tom indicated, if you have any questions regarding thicknesses or coil widths or the likes, definitely contact ArcelorMittal's representative in your particular company. We do have another question here regarding, this is for you, Parth. Is there any data to support the hydrogen embrittlement / hydrogen intake susceptibility during hot stamping of UC Board 2000?
Yes, we have the data. We have data available for hydrogen. If you need, you can contact me directly, and we can discuss. Very good.
Okay. One more question. This is for you, Tom, I suppose. There's a gentleman here that they say they use the Argus to confirm formability for cold stamping processes. Can this system be used with this hot stamping material, or does strain have to be confirmed in a different method?
The applicability to the Argus system is a little tricky. It is absolutely something that's being worked on, but as you can imagine, the gridding that's required or used for cold stamping is a level of difficulty more difficult for hot stamping. It's not impossible. It's actually different strategies are being used sort of in academia right now.
Okay.
But again, I hate to say this is sort of a default. If it's something you're struggling with, please contact us and we can sort of discuss some of the strategies that are out there. Basically, what you're trying to do is create something that'll survive the hot stamping process. But I'm hearing, different smart ideas every day So it is something that's actively being worked on.
Great. One more question. How do we get rid of twisting of A-pillars with patch and hot stamping? Again, that's a very specific application. So
Yeah. Yeah. So in the oven, obviously, if you have, let's say patch, your center area or whatever end area you have patch in, and the other area doesn't have patch, it's gonna heat ununiformly, right? So basically, you have to heat them uniform. If that's not happening, thermo boost, we have recently, that's what I was earlier speaking to about thermo boost. Geometrical distortion, it can help you with the geometrical distortion. If you're having issues, if you use thermo boost on a patch area, it will get rid of those geometrical distortion issues.
okay, well, that's a good lead into the next question, because there was a question here from the audience saying, is there any health/environmental issues with the thermal boost when it evaporates? Is there, can you guarantee that there is absolutely no residue on the part?
Yes, so we have evidence that there is no residues on the parts after you heat them. Health and environmental issues. Again, we haven't done a huge trial, but we have some laboratory trials data available for a different, gases and all. So we can discuss that if needed. We have some of the lab, but on a mass production side, it will be very difficult, because in the let's say in the plant, if you want to do some study how much gases it evaporates, it will be very difficult unless you have a dedicated exhaust which collect all the gases and residues. That might be possible, and it might be different from a stamper to stamper. But again, from the laboratory perspective, we haven't seen anything. On a residue sites, there is no residue after you heat them.
Okay. Is it available right now? I mean, is this ThermoBoost product available in production right now and commercially?
Yes, it is available from our mill in North America. It is available.
Okay.
And
there's a question that says how to achieve black AS coating. Like passivation, is that like, how do you achieve that? Is it like passivation? Are you passivating the surface?
no, it's so I think the question is regarding thermo boost, right?
Yeah, it probably is. Yeah.
Yeah. Okay. So this is basically a roll coat. It's a black paint, and you're just roll coating on the aluminum silicon. So you have currently aluminum silicon steel, aluminum silicon coated steel, and you just apply a black paint on it using roller coat.
I see. Okay. Okay. There's a comment here that says, in my experience, the aluminum silicon coating results in wide random variation in contact resistance to spot welding. This is the primary impediment to welding of those materials. Is there any new research about this huge problem?
Okay. So basically, I think question is regarding contact resistance of. So obviously, like I mentioned earlier, if you have a in your coating is different. Let's say hot stamping process, as I was earlier mentioning, that as you heat them, your coating get mature alloyed, right? If you have different IDL, if you have different coating thicknesses, right, it may have different impact. Because coating ultimately impact, it has a really good contact resistance, right? It creates a lot of heat, right? And that might create an issues. Is there a new study available? I can check it for you. You can contact us, and we can discuss in details what exactly the problem is, because problem could be different. When you have a part in flange area, if you have a higher thickness coating, then it could create more problems. If you have a low thickness in the side wall, then it may not create a problem, depending how your thickness is spread out across the part. If you have higher IDL, it could create any issues, but depending on a problem.
Okay. For laser welded blanks, are the laser parameters significantly different from typical cold rolled?
I'm not sure if the question is regarding doing a laser welding or stamping itself. I assume laser parameters like so if we talk about welding for aluminum silicon, obviously aluminum silicon, if you have too much in the welding, it could create a problem. Typical cold rolled, I'm not sure if that's I didn't get the question fully.
I suppose the question really refers to if you want to have laser welded blanks, like for example for an MPI approach. Do the parameters for the laser welding of those blanks are there any different than if you would want to do a laser welded blank of just cold rolled steel?
Certainly different. We would, I think, direct that question towards our Taylor Blanks division for that discussion. But yeah, I mean, absolutely. Not to mention, you know, the ablation process is something that needs to be considered for the aluminum silicon coated products for laser welded blanks. So that's, you know, one fundamental difference that would be different between using it for press-hardened steel versus cold stamp steel. But that being said, you know, from a laser welded blank standpoint, there are some significant advantages to the PHS family of products within laser welded blanks. So that, you know, should be part of the discussion as well.
Very good. Very good. And if for the participant who submitted this question, you know, if you want to contact either Tom or Parth, and they can direct you to their laser or their Taylor welded blank group, who have a lot of experience with that. Another question or comment, as well as a question, that there's some softening at near the fusion boundary observed for the 1500 grade. Should that be similar for all grades of PHS? What should be the governing factor that affects this softening?
Yep. Okay. So again, ductile 1000, usable 1500, usable 2000, they're all Martin stick product, right? So when you spot weld, you know, you will have a nugget, right? And you will have a softening in the surrounding area and haze area because of the annealing, right? Because the haze area temperature is below AC1 temperature, as I explained. And that's why the softening is occurring.
There's another thermal boost. Says about the thermal boost, I assume the thickness blanks, that thicker blanks from a Taylor welded blank can use thermal boost, while thinner will not. Is there any limitation there for the laser welding process?
Yeah, so if the question is that can we use for thicker, the answer is yes. I don't think there's any limitations for laser welding process. You can do thinner and thicker unless if there is it's compatible with the laser welder. So basically, if you have a blank of thermal boost, you can weld. You can weld with LUC, regular LUC, no problem. You don't have any issues.
And I'd add maybe Parth too that I think the best strategy is to look at the entire laser welded blank itself strategically and decide what application of thermal boost best suits that particular application. So it will absolutely matter, like the thickness difference, the products involved, and all that type of thing. So there is something that there's a skill involved, I think, in coming up with the best strategy and application for thermal boost.
Yeah, no, I think the question was more about can we use for thicker, right? So yes, you can use for the thicker material, thinner because it's going to heat faster anyways, right? Compared to the thicker material. So the strategy should be used for the thicker material. How thick and how thin, that again, that's there are a lot of parameters that you have to consider, including die design, right? How you're going to quench them if you have too much gap thickness, and then you have to talk to the tooling guy as well, tooling designer as well.
Okay. Question is there any tempering required after, or temper required after hot stamping?
For thermoboost, no, I don't think there is any tempering required.
Hesham, was that just in general or thermoboost related?
This seems to be in general, yeah.
Oh, in general, oh, okay.
In general, no. I think that's one of the, and it's related somewhat to the springback advantage of the PHS grades. I often look at it from the standpoint of you're kind of creating a new material at the end of the hot stamping process. So those residual strains, that cold working is really something you don't have to deal with in any way like you do with cold stamping.
A little bit more specific question here regarding, I think it's a specific application of trying to spot weld DP590 and PHS. The question is, will the nugget strains, will the weld nugget strains be different in cross section?
Strains will be different. Okay, that we have to look depend on thickness, right? So we have to look in the specific what thickness he's talking about, right? Heterogeneous, right? It's because it's a heterogeneous, it's not homogeneous, right? DP has a different coating than the PHS coating, right? So it will change the parameters.
Okay, I'll have so a few more questions because there are a whole bunch of them. Any special recommendations on trim cutter steel clearance and lead angle? Or is it the same basically for the base material?
Sorry, go ahead, Parth.
Yeah. So again, I'm not sure if he's talking about the cold steel or after hot stamping, right? That's not specified. So I'm just gonna assume that maybe he's talking about the blanking process.
I would assume so, because it would be very difficult to use cutter steel later on. Yeah.
I don't have that answer. What exactly the clearance, for the cold stamp. We can get you those answers if you want. I don't have that, answer today.
Question: are there any more developments on ductive ore besides the 500 and 1000?
Stay tuned.
Yeah, I could have guessed that answer, Tom. There are several questions here. I'm going to defer to Brian. Should we continue on with a couple of more questions, or do we just defer and tell our audience to contact Parth or Tom directly with their specific question?
Yeah, I think we've reached 9:55. I would recommend anybody's questions be directed to Tom and Parth.
Okay, so I do apologize, folks. I mean, you really got engaged in this, and it's really a great topic, and you had a lot of great questions. And for those that I wasn't able to get to, kindly send them to Parth or Tom. The email addresses are shown on the screen, and I'm sure they can get back to you with the answers. With that, I'm going to hand it back to Brian.
Thanks, Hesham. Tom and Parth, thank you very much for a very insightful presentation. Appreciate everyone's attendance and really thoughtful questions. Again, Tom and Parth, their email addresses were available there. Please do reach out directly. And if you've not already done so, mark your calendars and register now for Great Designs in Steel, May 21st. And you can register and get more information at greatdesignsinsteel.com. Thank you for joining us. Stay tuned for additional webinars and have a great day.